Here I'm going to give a short introduction and overview to AVR and SAM development tools, their larger context within the Microchip tools ecosystem. Start software content and IDEs will be distinguished in terms of how these pieces fit together. And finally, Atmel Studio 7 is introduced as an integrated development platform. From the Microchip website, microchip.com, design support, development tools, here we can see a link about AVR and SAM. To get an overview though, first click here on Tools Overview, and here we can see a matrix of different development tools by major MCU product line. Under AVR and SAM, we can see that the IDE is Atmel Studio. AVR and SAM GCC compilers are integrated as part of Atmel Studio 7. But if you'd like to run the GNU toolchains as standalone tools from the command line, you can install these packages. Atmel Start and the software content are distinct from one another. Atmel Start is a tool to help you select and configure software components. It has two entry points, either creating a new project or browsing examples. If you create a new project, you're able to give both hardware requirements as well as search for certain software requirements. And Start will help find a list of appropriate MCUs for your design. Alternatively, you can enter through browsing examples. Here the examples with a green light bulb are getting started examples. These tend to have video series and hands-on training linked through their user guides to give you an overview of how the system works. If we go about, we can see the Start user guide. Here you'll find another description of the different pieces of the system and how they fit together. The main focus of the Start user guide is the different configuration screens that you will see as part of Atmel Start. Also note that the output from Start can work with a number of various IDEs besides Atmel Studio, such as IR Embedded Workbench or CAL Microvision. You'll also see an API reference manual, both for SAM and for AVR, describing the actual software content. Let's have a look at Atmel Studio 7. Studio 7 is an integrated development platform for developing and debugging AVR and SAM microcontrollers, whether you're writing in C, C++, or assembly. The Studio can be extended through the Atmel Gallery and Application Store, and also can import Arduino sketches. Within Atmel Studio, you can find the user guides for all the different components and plug-in parts from Atmel Studio itself, Data Visualizer, Visual Assist, and many of the other pieces. You'll find an overview video series here under Getting Started with Atmel Studio, where there are a range of videos covering all aspects of the Studio. For understanding bare metal development with AVR, you can find a Getting Started video series, which is fairly comprehensive and covers a lot of the basic development of AVR using datasheets and application notes, etc. Download extensions opens the Atmel Gallery, extensions and updates, and finally you can download certain documentation and user guides and make them available offline. So I'm going to give a short overview to AVR and SAM hardware tools and debuggers. We're going to talk about the debugging platform and user interface, the Explain Development Kit platform. We're going to talk about in-circuit debuggers, namely the Atmel ICE and Power Debugger. We're going to introduce the Data Visualizer, which is a user interface for our debugging platform. And this is used to visualize data and give insight to the application, as well as analyzing and correlating power consumption to code. So let's first start by introducing the explained building blocks. So in the explained platform, all of these kits are USB powered and recognized by Studio. In addition, they also all include embedded debuggers to run, step, break, and visualize the code. The kits as well tend to be modular building blocks which combine with extension shields and clicks. The Mini is Arduino compatible, while the Pro supports extension and clipboard adapters. Looking at the overview of this development kit platform, you can see the Mini Embedder debugger is on the Nano and the Mini, and the embedded debugger platform is both for the Pro and Ultra, but also the same functionality is available in the standalone debuggers, the Atmel ICE and the Power Debugger. All these debugging platforms communicate over Simsys DAP to the IDE, Atmel Studio, but this also supports IR and ImageCraft as third-party IDEs. If we're looking at the data visualizer, the Mini Embedded Debugger series supports a virtual comport, whereas in addition to that you get a data gateway interface with the Xplane Pro, Ultra, as well as the standalone debuggers. In terms of the Atmel ICE is a standalone debugger for all AVR and SAM devices, and all non-high voltage AVR and SAM programming and debug interfaces are supported. There are 3 different editions: PCB only, basic with common cables, and a complete with all cables and adapters. The standard Simsys DAP debugger, and so it works with any front end supporting Simsys DAP, and there's a published communication protocol. The Power Debugger has a number of major use cases to supply and measure power of the application, separately measure MCU and solution power, measure the power of a USB application, as well as visualize and correlate application data. I'm going to take you through some of these. To emphasize that this has the same program and debug capability as well as the Atmel ICE, but also gives the ability to analyze and correlate power consumption to code. So the way it does that is it gets DGI application data from the application. We're going to show you some examples there. Here we have the AVR and SAM debug headers. We have a target supply voltage. You can power your application. And then there's 2 current measurement channels. Here you can see channel A is up to 100 milliamps, and channel B is a high current channel of up to 1 amp. You can also power a USB target. So if we have a target such as this board here, which looks like an Xplane Mini, we can see that we can make some connections to measure the board's power consumption. We can still have a debug connection through to Atmel Studio, for example, or a third-party IDE, and we can also have some GPIO instrumentation. For example, if we use the GPIO, we can, in this case, we are instrumenting the code to add markers for our power consumption. And so in this case, we are ensuring that we toggle the GPIO along with the switch pressed, and you can see that this correlates with the power consumption of the MCU waking up. In this example here, I'm showing a serial correlation because I'm using an ADC result put on the COM port, and you can see that the current spikes associated with every UR transmission of an ADC sample. And finally here, showing how the correlation of program counterflow and power consumption. So double clicking a sample will open the editor and highlight corresponding line of code. So from the Microchip website, under design support, under development tools, I can see software tools for AVR and SAM, and here I will see a homepage of the data visualizer. And this data visualizer, I can have a standalone version, or I can download an extension to Atmel Studio. In terms of the hardware kits, I can see a debuggers page, and here I can find the Atmel ICE as well as the Power Debugger. In the next video, we'll do some more practical demonstration of some of the data visualizer features using the Power Debugger as well to understand the application. So I'm going to be giving an overview of the data visualizer, covering some of the major features of the Mini Embedded Debugger and the embedded debugger, and the differences between those in terms of what we're able to get in terms of data from the microcontroller, as well as how we're able to visualize using the data visualizer. In the process, I'll also show an overview of the user guide and how to use it efficiently and effectively. Okay, so the demo that I have is a low power demo with the ATtiny817. We're using an RTC periodic timer starting an ADC conversion via the event system and then sending the ADC result on the UART. The ADC pin we use is PA1, which is connected to a pot between VCC and ground. The UART is automatically available on the embedded debugger CDC. On the X-Plane Pro, a similar connection with the pot, and the UART is again automatically connected to the EDVG. On the X-Plane Pro, there's additionally the explained analog module. This allows us to measure the MCU and or the I/O. The I/O would be the board and anything plugged into it. So in Studio, I'm able to access the data visualizer under the Tools menu, data visualizer, in which case it opens in Studio. In general, when I'm working on a single screen, I prefer to use the standalone version of the data visualizer. So here I'm still with the mini embedded debugger. And so it's quite normal for this to stay blank here because this is the data gateway interface. And you can see that there are two inputs. The one is the serial port and the other is the DGI. So this application runs at 57600 and connecting. I can see it opens a terminal and I can see that there are values coming out. Now if I want to graph, let's first click this question mark here. And here I get an overview of the major use cases of the data visualizer, including power debugging, etc. If I click on visualization, graph F1 here I am more in the context of the specific graph module, and I don't need to know too much about it, but I'd like to just see an example of how it's configured. So here I can see that basically once you have something that you're wanting to graph, you drag it into the plot and your data starts flowing. So what I'm wanting to do is double click on the graph and drop my serial port into a plot here. Okay, and then my data starts flowing. Now I'm going to scroll by time and points. And just stop it by pushing spacebar. Now I can add some horizontal cursors and notice that the readings stop below 100 and above 200 automatically fit to Y, because I know that this is this full scale of my application. So now I can see that there's some kind of limitation in the ADC. We're just getting readings outside of this particular window. Okay, so now it would be nice to understand the power consumption of the application and maybe some more things about it. But that's all I can really do on the mini embedded debugger. There's a graph and a serial port. So I'm going to just move the application. So just disconnect here. And I'm going to unplug my mini embedded debugger and take my power and ground, plug it into the other kit, and now connect via the 817 X-Plane Pro. So now I can see a new COM port comes up, which I can connect to, and re-clicking, so embedded debugger, and programming the part, going back to the data visualizer. I see that I have the same functionality as before, and in addition I can connect to the DGI interface. So the DGI gives me a number of different interface options: SPI, TWI, GPIO and power. I'm going to just look at GPIO and power and click start, and you can see immediately I get some information here. Now I don't actually want my GPIO on this graph, so I'm going to uncheck my GPIO, and I'm going to drop a separate graph for my GPIO. I am sitting at between a microamp and much less than that when I'm not transmitting. You can see that there's two DGI GPIO. PB6 is DGI GPIO 1, and PB6 over here, I set that pin just before I start transmitting. I put it in the TX data register, and then here this while waits until the transfer complete interrupt flag, and then I clear this pin. So what I'm actually doing here is measuring the duration of sending that byte of data at 57,600. Synchronize the graphs, spacebar to stop, and now I can zoom in. Firstly, you can see that the power spike correlates to sending the data, and if I show cursors here on this graph, I can see that it takes 176 microseconds to send the character, and also I can see that this is the bulk of my power consumption. In this video, I'm going to discuss the installation and updates of Atmel Studio 7. What are the choices that you make during installation? Notification updates and installing support for the latest devices using the Pack Manager are also covered. We'll start from Microchip's homepage, Design Support, Development Tools. Here we can go under AVR and SAM Dev Tools for the Atmel Studio IDE and scroll down to find the download link. There are two options of an installer. One which is offline, which includes everything, and online installer, which gives you some choices, so you have a higher granularity in decisions about what gets installed. So I'm going to run the web installer. So this little exe is just a bootstrap. Here I get to decide what major families of devices that I want to have installed. I'm going to use just AVR and SAM devices. This choice is for the Atmel software framework ASF3. Since I'm using mainly Atmel Start with ASF4 and also AVR code for AVR devices, I'm not going to install this. The installer checks if any Windows updates are needed. Here I get a warning that I'm recommended to update, but I don't have to. From this point on, you can go and get a cup of coffee. It might take a while, but you've done all the clicking you need to do. As Studio is open for the first time, I noticed that there are a couple of notifications. So here there's an update for Atmel Start and an update for the data visualizer. So this opens the Atmel Gallery extension, and I must go to Available Downloads, and here I will see the update. Note that here I can see all the different components that are installed as part of Atmel Studio, and I'm able to copy to clipboard, which will actually give me a full list of everything installed. If any new devices are released for families of microcontrollers that you have installed, you might get notifications here. So then you'll open the Pack Manager. You can see new devices which are available, some information about the device, and you can choose to install it. In this video I'm going to talk about the Atmel Gallery and extensions to Studio 7. Studio 7 is quite a modular platform, and much of the functionality actually comes through in the form of extensions. So I'm going to talk about some of the default extensions, certain popular extensions, and then also other extensions which I just happen to use in the series and in my daily development. I'm also going to show you how you can connect the Studio options for the tools to the extensions which are installed. Let's have a look. Under Tools, Atmel Gallery Profile, I can see my profile. If I don't have a profile, Tools, Gallery Profile. If you're a new user, you'll click here and you'll fill in some basic information, confirm your email, etc. Then you'll get a profile. And now I can go to the extensions and updates. So there are a number of default extensions. So these are installed extensions that I have. Atmel Kits enables the active kit detection that we have. Atmel Software Framework is delivered as an extension, as is Atmel Start. A lot of the functionality here is covered in the Start integration video. The toolchain provider, for example, so if I just click on the package reconfiguration, this is essentially that extension. So I can see here a list of the different toolchain options, and if I want 8-bit C language, I can add a flavor to the installed toolchain. The data visualizer is also used later in the series, and that is a default part of Studio, as is Visual Assist, which is basically the editor that we use. Note that with all the extensions you can click more information, and for instance here you can get an overview video of Visual Assist, although we will cover it more in an embedded context later in the series. Atmel Gallery, you can also browse extensions directly online, gallery.atmel.com. You can get more information about certain of the extensions. One of the popular extensions is the Arduino IDE for Atmel Studio, and this supports traditional Arduino development directly within Atmel Studio. So some of the available downloads, the Luther library, a lightweight USB framework for AVR, CodeVision is a C compiler and graphical configuration wizard also for AVR. FreeRTOS and Trace is very useful when you're using FreeRTOS and can offer some graphical tracing of RTOS threads. Nagi is very useful when used with the Atmel software framework, that it grays out all the code which is not defined in the project. The framework uses a number of if, defs, etc. Just note that Atmel Start generates ASF4, which is separate from the Atmel software framework you see here. So again, if I go Tools, Options, here I will see a number of elements, for example with Atmel Start, and many of these are actually related to the extensions that you'll see in the options here. Note also that there's a partner website, and if you'd like to extend Atmel Studio 7, here's an XDK to get going. In this video I'm going to talk about the integration of Start into Studio 7. How do we create an Atmel Start or Atmel Start example project directly from Studio, and also how do we do iterative development, reconfiguring Atmel Start projects and handling diff merge, etc. And also how do we generate AVR code project documentation. So within Studio I am able to File, New, Atmel Start project. And here, just like on the web, I'm able to have both hardware and software requirements for my project, which helps me filter down the number of suitable microcontrollers on which to run the project. Alternatively, I can also search for example projects. And here I can filter just like on the web with a number of different options. If, for instance, I'm interested in the distance measurement from this application note, which we can find online, I'll download this project. So here the project is actually open and I can navigate and understand how it's been configured. And for instance, I'm going to have a look at the ADC and I can see that that is set up to run in 10-bit mode. So now I can generate the project, and at this point it'll create the project in Atmel Studio. So now our project is created and we can start working in development with it. So one of the things to have a look at is there's a Doxygen plugin to generate documentation. And here I can see documentation of the AVR code, which is specific to this project that we have created. So now if, for instance, I decided that I wanted to modify something, and as I'm playing around I decide that I'm going to just update the ADC resolution, and I see that there's an option of 8 bits. So I update the resolution. Now I want to regenerate the start project, reconfigure. So here we notice that the ADC should still have the 10-bit resolution here because it hasn't been changed on this side. Let's leave it as it is and see how Start will handle this difference. So as you can see, the files are downloaded and it compared with the local project. We can click on a view diff and we can see the line that we changed, and we can accept that if we want, so that we go back to the 10-bit resolution. One thing to note is that in order to adjust any of the settings of anything that we've worked with today with the Start integration, there's an Atmel Start section in the options. Here is where you'll point to the exe from Doxygen once you've installed that, if you want the project documentation. File compare, there's some description here about using WinMerge and how I've linked that in. And then the settings, here is the URL for Start. And one note about the editor, since we have a fairly large project open, note how useful this list methods in current file is to find a certain function like the ISR, for example, and also using the Visual Assist outline mode. So here you can see all the functions and easily navigate the file. In this video, we're going to show you the various options of creating a new project in Studio 7. Going through the various options in the standard new project dialog, also talking through ASF3 projects and the create new ASF example project, and then looking at ASF4 and start projects, which is also possible in Atmel Studio. Note that the code that Start generates for SAM is ASF4, and so that is distinct from what we see in ASF3. The standard new project dialog comes up as such, and we can see that there is a standard C executable project and a C++ executable project. Then you get a C static library and a C++ static library. The C executable or C++ is probably the most common project type that you will use for a bare metal project. A static library, you create pre-compiled libraries to link to other projects, and this tends to be to use same functionality or to share a kind of core company IP across various products. So for example, Atmel uses this static library for our peripheral touch controller, one of the more unique peripherals that we have for touch applications with buttons, sliders and wheels. So the touch library itself, which configures sensors, adjacent key expression, noise handling, gain and filter levels, etc., which you all configure in a touch application, that gets compiled as a static library project as a .a file and then linked into the project. So the create project from Arduino Sketch is going to be covered in the next video. Basically, it creates an Atmel Studio project from Arduino Sketch files, and there are two projects, a Sketch and Arduino Core. The other options, new example project, this here relates to ASF3, and you can see that it's 3.34, so it's ASF3. There's quite a range of examples that you have here by different technology categories, etc. And if you create a new project with an ASF board, this basically is a board support package of ASF3. The focus more is on Start at the moment, and you can see you can create a new Atmel Start project or a new Start example project. And here you can filter on hardware requirements, as well as searching for software, which includes both drivers and middleware. The other option was the Start example project. Here again, filtering by boards or categories with an open search. If you're not sure what either of them does, you can just click the user guide and get an overview of what happens in some of these. These getting started projects are a bit of a special category. Those tend to be linked with training materials, etc. So if we select a basic application, as I said, for bare metal projects, we're probably just going to use a C executable. And then after selecting project, you get to select a device that you're interested in. You can select by family, and if we want the 817, we create a project as follows. Thank you. In this video, we will demonstrate the kit connection capability of Atmel Studio, the active kit detection with the excl Pro. We're also going to take you through the device programming dialog, do things like read device signature and target voltage, check a device silicon version, and the fuses, or the equivalent of the config bits from the PIC world. Okay, so in Studio, I plug in my kit, which is an ATtiny 817 excl Pro, and I will get a welcome screen popping up. So note here that we are able to create new Atmel Start example projects or create a new Start project using this board. What this does is opens Atmel Start with a filter of the board, and you can see the different projects available here. Notice also that extension boards, which are plugged in, here a Bluetooth extension board with BTLC 1000 or the IO excl Pro, are also detected. So now with the kit connected, we can go directly to the device programming, and we can see that there's an embedded debugger tool picked up, and we apply. And here we can read device signature and a target voltage. Here's some information about the embedded debugger and the device. Note that we can see the silicon revision of the device here, which is quite useful sometimes if there are any support tickets. Memories, you can program the flash and EEPROM files separately, or even the user signature row. And fuses are the AVR equivalent to config bits in the PIC world. For instance, that the oscillator is set to run at 20 megahertz as opposed to 16. We can see that there was the brownout voltage detection, etc. Also, lock bits when we're ready to go into production, or there's actually some production file. I'm going to talk about the differences between what you might be used to with PIC, with everything in the hex file, and what you have with AVR, where you have the flash in the hex file, but the EEPROM is in a .eep file. Also, you'd be used to seeing the fuses information included in the hex file, and I'll just show you a little bit about a project setup later in the video to explain these differences. Creating an empty project for the SAM L21, I can show you a similar process here. Here the device information is the L21J. Memories, note I don't have EEPROM showing up here, and in most SAM parts we have EEPROM emulated in the flash. Here we have the fuses, and there's a security bit option. I did go through the different types of example projects in another video. So we just need a C executable project for the ATtiny 817. And here we can associate a tool with the project. And that would be the same thing as if we'd gone right click and project properties. So since I'm in the project properties, I can click on toolchain, and here under general and output files I can see a number of different output files which are generated by this project. And note as well that as soon as I start without debugging, which programs the part, I can see this list of files here being generated. Firstly, the dependency list is also generated, and I can directly open, for instance, the device header file, and I can see all these different options here. So to understand what these different file options are, the EEP file is an EEPROM content at program time. The ELF file is something which contains everything, including EEPROM and fuses. The hex is just the content of flash at program time, and the list LSS is the disassembled ELF file. Map file is a linker map file. What did the linker do? Decisions about where to put things. And the SREC file is the same as a hex, but in a Motorola format. We're ready to start writing code. In this video, I'm going to take you through all the various bare metal programming references that we tend to use when using Atmel Studio 7 with a specific board. So how do we access these? What do we use each for? And I'm going to use a very simple context of turning on a LED and then blinking with a delay a little later. I'm going to use the device datasheet to get an overview of the peripheral, typically with a block diagram. I'm going to use the datasheet from IOView in a more specific context of understanding the registers of the device that I'm working with. I'm going to use IOView when debugging to test functionality and to understand the current configuration of the device. Kit user guides and schematics help me understand what is again connected to the specific pins, so I can use that functionality. The editor lists a lot of what is in the device header files, so we understand the structs in the device header files and how the editor helps us use those. AVR libc gives us some basic functions to use with C libraries with AVR, such as delays, etc., and using interrupts. And then finally, Atmel start is quite useful just to understand the default configurations of the clocks, etc., in a very graphical kind of way. And I'll use this even if I'm doing bare metal development. Okay, let's get going. I have this board plugged in, so the welcome page is up. Clicking on the device datasheet page, I come to the 817 product page. Here, under documentation, I can find a complete datasheet, and under development tools, I can choose the kit that I have, and I see that there's the 817 Explain Pro. And here I can see the design documentation, a zip file, and the Explain Pro user guide. The user guide has much of the same information that I will use in the schematic. So once I have got that information and downloaded it, here you'll see the data sheet, the user guide, and then the design documentation. So what I'm going to start with is the data sheet, and if I'm looking at ports, the kind of thing that I like to look at the data sheet for is the block diagram. So I can see there's a pin control register on this port with pull-up enables, there's output and direction, and just reading down to the description here, I can see that the port registers have a data direction and a data output value. Okay, so this gives me an overview of how it works. What I'm going to do now is look for these registers in the I/O view. I need quickly a project for the 817. And note that I could also access the data sheet here. I can open I/O view, and here we can have a look at the port registers. To use more specific information of them from the data sheet, I would tend to go F1 on a specific register. And here I can see that writing a 1 to the direction configures and enables it as an output. So consulting the schematic of the kit, I can see that the user LED is connected to port B4. So I must set port B4 as an output, and I must set it low to turn the LED on. If I start debugging and break, I'm able to directly start manipulating these register bits. So there I can see bit 4, the direction, and actually my LED has come on straight away, and as I click this, the LED comes on and off. So now we've set it as an output. Now the out register sets whether the pin is high or low, and again, as I click on this, this turns it off because it's set it to a 1, which is high, and clicking here again, we can turn the LED on and off. So we are pretty confident in the functionality of what we're trying to build up, and we can start to use this, write some code. So port B dot, and we're wanting to set direction. So here we have a suggestion list in the editor, and actually in the next video I'm going to be covering a lot more of the editor features and how they help us write code. For now, we'll notice that as we start typing, there's a context field of port B where we currently are, and then definition field which shows how this is defined. So if we click direction, so you can see that that's a certain register also within a port struct, and if we go to the definition with Alt-G or clicking go, we can see that we actually open up the device header file. So here, this list of registers is pretty much what we had in our suggestion list, which came up in the editor. And you can see how the device header file is referenced by the editor. So let's move forward. There's a pin bit mask, and setting the direction, stop debugging and program the code. And the LED is on as expected. Now what I'd like to do is toggle it every 500 milliseconds, and AVR libc is going to help me do that. And you can see AVR libc is a free software project, provide high quality C library with GCC on Atmel AVR. Clicking on the user manual, I can see the library reference, delay, and here I can see what I can do and functions available to me when I use this, and I can see that I need an include util/delay, and there's an FCPU description. First including it, util delay, and now I can use one of the functions, and I can go port out toggle to toggle the pin. Okay, so now compiling this code, I get a warning of this FCPU not being defined. I'm going to find a solution for that just now, but for now I can program and I can see my LED is blinking. Well, viewing I/O view again while debugging, I can have a look at the clock control, and I can see that, okay, my clock is set to the 20 megahertz internal oscillator, and the prescaler division is set to 6. and so then I have a 3.333 megahertz clock, so I could define the CPU, the frequency here directly. But I'm also going to show you how you can use Atmel Start to do some of the basics. So if I create a new project for Atmel Start for the board that I have, the clock diagram here gives me quite a good overview, and here we can see that same default frequency. Also, if I click View Code and under Config, I can find that define that I needed in my project. Also note that it's quite useful under Pinmux to show the board labels, and here I can see how the board is laid out with LED or the UARTs, etc. So going back to my project, adding the define of the CPU in and rebuilding my project, I see that now we have no warnings. So that's been a bit of a whirlwind tour of the different programming references typical for bare metal development, how we use IOView to test functionality, the role of the datasheet, both F1 linked through the IOView or using the PDF version, kit user guides and schematics, device header files, and one thing to note is there's a very good application note, AVR 1000, describing the structure of these header files, well worth reading. Then the editor. In some of the next videos we will cover much more of the editor features, but we just gave you a little bit of a taste today. Thank you. Okay, so I'm going to give you an overview of the Studio 7 editor. We'll carry on from the basic place where we were at the end of the programming references. We'll turn on a LED now, but now when a switch is pressed, first we start off polled and then introduce pin change interrupts. And this is our basic context to explore suggestion lists and the ways of using these efficiently, enhanced list boxes, how to quickly find enumerated parameters, etc. We're going to use Visual Assist code snippets, refactoring code, extracting functions or methods, introducing variables, contextual renaming, and surrounding with regions. But first we're going to learn some basics about reading code. So we have the ultrasonic distance example open, and it's great to have a fairly large project and files open to appreciate some of the features of reading code. First of all, I'm going to enable map mode on the scroll bar, and this enables me to kind of view the code as I'm scrolling. List methods in file. This is very useful for navigating large files. There's another option of doing this as well, and that is Visual Assist Outline. So Visual Assist is basically the Studio editor. It's a plugin to Studio, and here we can have the outline view. Of course, everything that I open, I'm going to go from the quick launch bar, and here I can see everything that is in this file. The typical thing that we're going to need to do, for instance, in main, and we're initializing the system, Alt-G, we'll go to a definition, and here we can find all the functions again, ADC init, Alt-G, and so I'm navigating up and down the levels of the file. So here we are where we finished before, and here from the schematic we have this list of things that we know and what we're trying to do. Initially we're going to remove all of what we did with the delays because now we're using a switch. We know that we need a pull-up resistor on port B5, so as before we can just use the port B, and have a look at this in the IOView, and in the pin control register, that's where we have the pull-up enabled. That's quite useful to have that as we reference and start writing some code. So we want port B pin control. It's pin 5 and it's pull-up enable. Now what I'm going to actually do is just to show you that I can go P, so you can kind of use acronyms as you're using this. Another thing I can go is control space. Now control space brings up all the options, so now I can kind of scroll up and down here, but what's important is I can go by type. So here I can see that that's an enum or a type def. Here I can find the actual enumerated parameters, definitions. If I go back, I can get some more options here. Here I can get global variables, and here I can get all the different structures. So we know that it was port pull-up enable, and we can just use that. So continuing to write some code, we're going to use Visual Assist snippets. We can go if else. We can right-click, surround with, and here's a number of these snippets. This is an editable list, so you can add if you use some others. We're going to check that the switch is low. Okay, so this should hopefully work. We can run the code, and now we can see, well, the LED is coming on when we push the switch. So code itself is not too readable, so I'd kind of have to introduce a comment, but of course comments get out of sync with code, and so you kind of want to avoid comments. And so I can extract a method or a function. I can say LED on, and as I create these, I'm just going to create function definitions for them and then move them to the end. Then the code becomes more readable, and you can see exactly what it's doing. You can see the functions and how they work, and then you kind of have a summary of your code. So what I'm going to do now is extract a function here which sets this, checks the state. So I switch get state, and actually you can see that that's a bool. So I should actually introduce a variable here. So now I have a choice. I could rename this bool to uint8, or if I leave it as it is, I'm going to need to introduce include standard bool as a header file. Otherwise I will get an error when I compile this because it's not a standard C type. So this function now is going to be LED set state. And we can see that the combination of having these function definitions and the code written in a very clear way so you understand what's happening, it makes the code more readable without the need for comments. So that was with the switch. So I'm just going to move the function down, which is related to the switch, and all these LED ones together I can say surround with region and LED functions. And what this means is I can just have this region in my code and then minimize it, or so that's quite useful as well. Another thing that I could do with these LED functions is right click, refactor, move selections to a new file and create an led.c. Note here that an led.h is already, which I'll have to just put in main. And then I'll move these function definitions to an led.h. The pragma here ensures that these are not included more than once. Okay, just checking on the functionality again. And everything's working as it was. Okay, so now the next step for us is to introduce interrupts. We want to use pin change interrupts here, and I want to go to the user manual, library reference, interrupts, and I can see that the header file is AVR interrupts. Say I must call to enable global interrupts, and I notice that the pattern here, all the interrupt vectors are underscore vect, so we're going to keep that in mind. Before we forget, we're going to enable global interrupts. And I need to now also define which kind of interrupt I want. And if I look at the pin control register, there are these groups of different types of interrupts. If I just open the header file, Alt G on something I know is in the header file, I can open the enum of all these different options. Because if I, for instance, go to the register summary of the ADC, for example, I can see that there's a number of enumerated parameters with these group bits. So mux pos, for instance, again in the header file, I could easily find the enum like that, and I can see this one would be for the analog comparator, and here this would be for the ADC. If I wanted to see the window compare enumerator, for example. So that's quite useful to navigate like that. So I've interrupt both edges. I'm going to create the interrupt service routine. It's with something underscore vector, and we know that we're on a port, and we can go underscore vector, and so we find our port B option. In this file, if you search for interrupt, there's hits all the way through the file. If I search for underscore vector, you'll find a section of the file where all the interrupt vectors are. I need to just read out the interrupt flags. And now I should be able to just move my functionality into the ISR. Compile, and the one difference you'll notice is that now my LED is on at the start, whereas and that's because before it was immediately getting polled, but now it's only waiting for a pin change interrupt, and then it works as soon as I start pushing the button. In this short video, I'll be showing off the AVR simulator. I'll be using 3 different options to set and clear different register bits, just to demonstrate the difference between a hardware read modify write, doing it normally in software, and then also using the bit addressable virtual port registers in some of the new Tinies. So I'm going to use the cycle counter and the stopwatch to demonstrate the difference between these, and also disassembly view so you can see how each of the code is compiled. And then I'm also going to simulate some interrupts using the simulator as well. Okay, let's get going. So I have the same project as I was using showing off the editor, and I am just written some code here where I am clearing a bit and then setting it. So this is the direction bit of pin 4, which is our LED, and so we're just clearing it and then setting it, and we're doing that in software. So I'm going to just show you quickly the data sheet. And so in the port of the 817 we have hardware read modify write through dedicated toggle clear and set registers, and those are these toggle clear and set registers referred to there, both in the direction and out. And then what we have is mapping of often used port registers into bit accessible I/O memory space. So when we look at virtual ports, the direction out, in, and interrupt flags are actually exactly the same as direction out, in, and interrupt flags registers in the port. So we can access them just having vport instead. And so we'll see if there's any difference in how this code is compiled. So as a starting point, I'm going to just associate the simulator to the project, and then I'm going to start debugging and break. So processor status comes up, but if that wasn't there, I can just go for processor, and there you can see that actually as we've started up, we've got 13 cycles on the clock. We can reset this and run to this point and this point and this point. So if we now run, we can see that we take 10 cycles here, another 3 using the hardware read modify write, and just 2 cycles using the virtual port registers. So if we had to look at the disassembly view, we can map these up next to each other, and we can show you that there's a fairly considerable amount of work done in software to clear and set bits. You can see that there's fewer instructions there with the hardware, and then with the virtual port you can see it's just a single instruction. Clears bit and IO register, sets bit and IO register, and you can see how efficient that is. So the next thing that we want to do is we want to see if we can hit an interrupt service routine. So the difference is here, now if the code is running, we can't really trigger an ISR, but so we kind of have to pause, just sitting pretty much in the while loop there. And if we go to our interrupt flags and set bit 5 and then run, you can see we hit our ISR. Now that we're in our ISR, we can try and step into some of the functions. And see the program flow. Thank you. So in this video I'm going to be covering some of the basic features of debugging in Studio 7. The project we're going to use is following on from what we built up in the Studio 7 editor video. So we're going to cover basic breakpoints, code stepping such as stepping into, over, out of functions, the functionality available to us in the breakpoints window in terms of managing breakpoints. We'll have a look at the call stack and see where functions are being called from and seeing if this call stack is as expected. Then in order to get the output that we expect, we're going to look at the compiler optimization in order to set it to a lower level. And finally, we're going to be covering a truly great Studio feature, being able to attach to target. This means launching a debug session on the selected MCU without reset or uploading a new application. So you can see exactly where it might have got stuck. So what the project basically does is we set up the LED pin as an output. The switch, we enable interrupts on both edges and pull-ups. Then here we turn the LED on or off depending on the switch state, which we get in switch get state. And all of this is triggered from the interrupt service routine. So let's run the program and see if it works as expected. We are going to left click just to set a breakpoint and then start debugging. So as the project starts running, you can see that it's running here at the top and also in the bottom left. And now if we push the switch, we hit the breakpoint. Now an interesting question is, will this turn on the LED or not? So we step over the get state and we can step into the function which sets the LED. And stepping again, we step into the LED off function. So we haven't turned on the LED. And I guess this is expected. Just running again to get back to where we were, since here we didn't necessarily have the switch as we actually checked to see whether the switch was pressed or not. So now if I hold the switch down as I step over, I can see that the switch state now returns a 1 where it was 0 before. Okay, so now I can set a breakpoint on LED on and basically hit that. And I do. So let's just introduce a window to help us manage some of the breakpoints that we have in our project. So I'm going to search for break, and I can see debug windows breakpoints. So there's a breakpoints window, there's a data breakpoints, toggle, new breakpoint, new function breakpoint. So where is all of these coming from, these options in the quick launch view? You can see that under debug, Windows breakpoints and data breakpoints, toggle breakpoints, new breakpoints, function breakpoints. So basically the whole UI of Studio is searched, which I use all the time, this quick launch bar. So let's open the breakpoints window. What I'm going to show you here is you can enable or disable breakpoints. For instance, I've disabled this breakpoint now. I won't hit it. I'm just holding down the switch, stepping over, so you can see my state is 1 and I don't hit the LED on breakpoint. Other thing I can do is go to disassembly, and here you can see it very neatly opens the disassembly next to the lines of code that we're working on. Okay, call stack. And this is actually only available when debugging. If, for instance, I stop debugging and try and look for call stack, it doesn't come up, and it was under debug windows and it's not there at all. So I need to be debugging, and then I can find debug windows call stack. So let us run and hit the LED on breakpoint, and here we can check the call stack and see that we are coming directly from vector 4. What is vector 4? Well, we should be coming from our ISR, right? So if we click here on the ISR, the definition, we can see that that is vector 4. And we can Alt-G and see that yes, port B interrupt is defined as vector 4. So our call stack is saying that we are coming into the LED on function directly from vector 4. And that is a little strange because we are actually coming from this LED set state function. In order to see the full path of how we get there, let's go to project properties. We have to stop debugging and then go to optimization. And let's try again. Holding down the switch, and I hit LED on, and now you can see coming via LED set state as expected. So now we'd like to show off that feature about attaching to target without resetting the MCU. So what we need is some kind of function which will only get called in certain circumstances. So I'm going to create a function, my mistake, and I'm simply going to call a while1 here, and what I'm going to do is just in this while1 call an ASM NOP instruction, because this can't be compiled out by the compiler. So now I'm going to just call this function. We should only end up here if we've triggered an ISR. I'm just going to program the part now, and now attach to target. And you can see that we're basically sitting in the main while loop. Whereas we program again, we trigger an ISR, and we attach to target. And here you can see we're sitting in this function. So you can see how useful it is to be able to jump in without having to reset the MCU. Okay, we're going to go on in the next video and cover some of the more interesting advanced features of Studio 7 debugging. Okay, so now we're continuing to investigate and play with some of the more interesting debugging features in Atmel Studio 7. So what we're going to do is we're going to take the project from where we left off, and we're going to revert back to polled mode. We don't need interrupts in this particular hands-on, and we are going to add some logic to the switch get state. We're going to call it states get logic, and we're going to add a previous state and an edge count as well. In the process of doing this, we're going to show you the watch window, how to view and modify variables. We're going to look at conditional breakpoints, and then also what we're going to do with action breakpoints is we're going to try and log the various state variables to an output window. So first thing to do is we are going to remove the interrupts, So the logic comes back into the while loop, and we don't need the ISR anymore. Next, we're going to modify the get state to a uInDate, and we're going to call it get states logic. So we need a couple more variables here. So we've added a previous state variable and an edge count, both UN statics. Now what we were returning is basically our current state. So as we read the current state, we can then check if we need to increment an edge count or not. Now we need to just keep track of the previous state. I'm just going to rename this to be previous. So just adding a logical constraint. Let's now debug and check the behavior. Just disabling breakpoints and running. So I can see a fairly irregular pattern here. I set a breakpoint and the program breaks. I can now hover over the edge count and see that the value is 47. I right click and can add to watch, and here I can see the edge count, the name of a variable, the value, and also the type of the data. Now here I can double click and actually change the value. So if I set this to 3, firstly I can see that the current state is 0. So 0 or 3 mod 3 is 0. The not of 0 is 1. So this will give a value of 1. So as I run now and disable this breakpoint and run, the LED would stay on. And it does. So now add some conditions to the breakpoint here, and we're going to right click, add conditions. What we want to do is check if the edge count is a multiple of 5 and if the current state. So the current state will be pressed, and that will give a positive output there. Enter to accept this. I can now test how this works. So running. And I can see the edge count value is 10 as it breaks. That's 20 the next time it breaks. And one more time. Just confirming I'm pushing down as it breaks on 30. The next thing we're going to do is we are going to set an action breakpoint. Here, previous state is current state, and here we set an action, and the action that we want to log a message to the output window. So previous state, current state, and edge count, and if we hit enter and then find the output window, and you can see that we continuously get updates of these variables. However, we can see it's streaming a bit fast, so let's rather, instead of there, only set a breakpoint where we actually increment the edge count. And now you can see that every time I push the LED in, I get 2 edge count increments. And so I have demonstrated the use of both conditional and action breakpoints. So as we continue to play with Atmel Studio's debugging capabilities and features, we're going to continue from debugging 2, and now we're going to change the clock frequency to 10 megahertz. The reason we're going to do this is to have a look at the configuration change protection registers so that we understand how to use those properly. So there we will use some of the IO view features. And we're also going to add some functionality to save data to EEPROM so that we can explore and have a look at some of the memory views. Finishing off with the watch window and how to cast a pointer to array so that we can view it. So let's start off by changing the clock frequency to 10 megahertz. So if I look at the IO view, CLK, and if I start debugging, I can read the current state, and we can see that we are at a 20 megahertz internal oscillator, and that by default our prescaler is 6 times, so it's 3.3 megahertz. So what we want to do is change this prescaler. So if we F1 on the main controller B, we can see that there's a prescaler enable and the prescaler divisor. So pdiv is what we need to write to. So we need to go to clock prescaler enable. So we also need to write to pdiv. So as we learned in the programming references section, Alt-G, open the device header file and just type pdiv, and here we can find the enumerator, and we wanted a divisor of 2. We OR these two together and read modify write, and let's see if this has been successful. So here we can see the prescaler is 6, and as we step over, it has not changed, and you can see that nothing has changed here either. So the reason is, as we have a look at the data sheet, that this is a configuration change protection register. So there's a special function to use in order to change these registers, and these functions are underscore protected write. This function, you can see, takes in a register and then the value we want to write this register to. So this is simply the register, and the value is what we worked out just now. And let's see if this works now. And stepping over, now you can see that the prescaler divisor has changed, and we have a prescaler divisor of 2. Okay, so in part 2 now, what we're going to do is we're going to try write some basic functions to access the EEPROM. As we do before, look in AVR libc and search for EEPROM. Here we can see a list of functions available to us, and also that the include is AVR EEPROM. So what we wanted to do was use one of these functions. Let's just use write block. And if I have a function, which I'm just going to use this as a reference here, I can also go F1, get the function specific documentation here. So all this is doing is copying from a source to a destination of a certain size. So I'm going to use this function. The source is from an array, and we've got a hello world. And we could write that from the source, which is hello, to, let's just give it a void pointer to 0, which is basically going to be the start of EEPROM, and we can use the size of hello. And let's write one more time, Now looking for the memory view, and the memory 1 view is what we wanted, and we can set it to different types of memories such as fuses, or what we're looking at is the EEPROM. So I'm going to run to the first EEPROM write, and stepping over you can see that it writes to hello world and it automatically updates, and stepping twice more we have now written the second line. So what we'd like to do now is actually just write a little function which can save something that we want to write to EEPROM. So this line which repeats, we're going to create a little function to write to EEPROM and also save. Now we can replace the EEPROM write calls with calls to the save function. And here we can see we are writing as before, hello world, and AVR says hi. Now the reason we created this new function is we wanted to show you Studio cannot understand properly the value of what's happening of this variable to save. Although if we do click on hi, for instance, here we can see exactly what that is set to, as is hello, but Studio can't evaluate save yet. So the way that we can do this, here we can dereference a pointer to look at the contents of memory and cast to an array. And now if we run to our breakpoint, you can see that the contents of to save are known up to the certain point. So what we tried to do here is to show you how to cast a pointer to a different data type so that it's more readable in the watch window.